Hello, class! So far we've only analyzed motion in one dimension. For the x direction, which is left and right, and the y direction, which is up and down. In order to start understanding how to analyze motion in two dimensions, we need to first understand the concepts of vectors and its application. Do you recall the definition of a vector and scalar? Correct. A vector has direction and magnitude, whereas a scalar only has magnitude. Direction can be indicated by the plus or minus sign in front of the number to provide information on whether the vector is pointing left or right, or up and down, or even north, south, east, and west. Direction can also be indicated through using degrees. The magnitude is the actual number or value without the plus or minus sign. Can you think of some examples of vectors and scalars? Great job! Displacement and velocity are examples of vectors because they have direction and magnitude. They point in one direction and have some value associated with it. Mass, time, and temperatures are all great examples of scalars because they do not have direction. There is no direction of whether time is pointing up or down, only a value is given. We use arrows to represent vectors. The head of the arrow indicates the direction and the length of the arrow represents the magnitude. Now we're going to learn about vector algebra. For example, let's say Mr. Gardner decides to walk 8 kilometers from the Hawk's Nest to the Eagle dormitory for a quick stop. Then Mr. Gardner decides that he needs to also check on Dio. So he traveled another 6 kilometers. What is the resultant vector of his trip? Yes, you're right, 14 kilometers in the positive x direction, or east. It's pretty simple to add vectors along the same direction. Let's do one more example. Let's say after Mr. Garner walked 8 kilometers from the Hawk's Nest to Eagle dormitory, he decides to turn around and grab a quick snack in the refectory. What is his resultant vector now? I can't fool you. Correct. 2 kilometers, but still pointing in a positive x direction, or we can say eastward. A vector not pointing directly in the x or y direction contains vector components, d1 and d2 in this figure. The vector component d1 represents how far in the x direction the resultant vector traveled, and d2 represents how far in the y direction the resultant vector traveled. Mathematically, d1 plus d2 does not equal dr. However, you can find the magnitude of dr through either using Pythagorean theorem or trigonometry. To indicate that a variable is a vector, a small mini arrow is drawn above the variable as shown above d1, d2, and dr. Recall Pythagorean theorem. A squared plus b squared equals c squared. We'll mainly use this equation to solve for c, or in this example dr, which represents the hypotenuse of the right triangle. Here's just a visual demonstration of adding vectors together with a method called tail to tip. In this example, 3 vectors are added together by connecting tail to tip. The only vector missing is the resultant vector. You can pretend the vectors represent a hiking trip. The resultant vector is the only one drawn backwards, meaning tail to tail and tip to tip. This makes sense because the resultant vector begins at the starting point and ends at the finish point. See if you can redraw this tail to tip diagram, but in a different order. You'll get the same result. Another visual demonstration is the parallelogram method, as seen in figure B. With a parallelogram, you can pretend that there are 2 ropes tied to a rock and pulled in the direction of V1 and V2. As a result, the rock will move along the resultant vector VR. As previously discussed, every vector on a coordinate system has components. Typically the components are labeled Vy and Vx, so Vx and Vy are components of vector V. The direction of vector V is defined by the angle in this example. Through using trigonometry and Pythagorean theorem, any variable can be solved. The most common equation we'll use for vector algebra is in bold on the right side. Please write down these equations for future reference. Here's perhaps a more complicated picture of explaining vector algebra, but before we dive into a problem, let's take a look at this. Let's say, for example, you're hiking in one direction along V1, and then you make a turn to hike along V2. What is your resultant vector, meaning the distance and direction from the starting point to the finish point of your hike, which is represented by VR? To figure this out with only knowledge of V1 and V2, use sine and cosines to first add up all your components in the x direction, which is V1x and V2x, and this equals the resultant component in the x direction, which is VRx. Then, add all your components in the y direction, which is V1y and V2y. And this would equal your resultant component in the y direction, which is VRy. Once you know VRx and VRy, you can solve for the magnitude of the resultant VR by using Pythagorean theorem and the direction by using inverse tangent equation. Don't worry if you don't quite get it yet. We'll do a couple example problems. But first, here are some steps you can write down on how to do vector algebra. Along with these steps, have those equations I told you to write down earlier nearby. First example. A mail carrier leaves a post office and drives 22 kilometers in a northerly direction. She then drives in a direction 60 degrees south of east for 47 kilometers. What is her displacement from the post office? The displacement is from the starting point to the finish point, which is visually shown below by using the tip-to-tail method. However, I find it easier to solve vector problems by drawing all vectors from the origin. So in this picture, D2 is brought down to the origin, and for now the resultant vector is not shown in this picture. Step 1 of vector algebra is breaking up any components at an angle into its components. Breaking up any vectors at an angle into its components. In this example, we have one vector, D2, at an angle with respect to the coordinate system. Step 2. Let's add up all the vectors in the x direction. The only vector we have in the x direction is D2x, but we don't know what D2x equals. However, we do know the value of D2 and the angle. With some trick, we can solve for the value of D2x. I redrew D2y as an orange vector so that you can see that there's a right triangle formed with the components. So D2 equals D2 times cosine theta. Now let's plug in some numbers to get 47 times cosine of 60. Then let's calculate, and we'll get 23.5 kilometers as your final answer for adding up all the vectors in the x direction. Now step 3. Let's add up all the vectors in the y direction. This time we have D1 pointing up and D2y pointing down. So we need to subtract D2y from D1. Again, like the x direction, we don't know what D2y equals, but we can figure it out by using trigonometry. So D2y equals D2 times sine theta. We can plug in some numbers and we get 22 minus 47 times sine of 60, which gives us negative 18.7 kilometers. We just added up all the vectors in the x and y direction separately to get 23.5 kilometers and negative 18.7 kilometers. What this means is you have the values for the components of your resultant vector. I'll bring up the resultant vector in the figure again so you know what I mean. 23.5 is the x component of the resultant vector, dr, and negative 18.7 kilometers is the y component. Can you see a right triangle formed with the components? Good, because we can use Pythagorean theorem and trig to figure out the magnitude and direction of the resultant vector dr. By applying Pythagorean theorem, we get dr equaling 30 kilometers. Notice how I didn't include the negative sign with 18.7. That's because it's squared and two negatives would cancel out anyways. When using inverse tangent to figure out the direction, you need to be aware of what quadrant your vector is in. Because when you use inverse tangent function, it actually gives you the reference angle. In this example, our resultant vector is in quadrant 4, and our reference angle is shown by theta, which equals 38.5 degrees. But since we're in the 4th quadrant, we need to put a negative sign in front of our degree, because it's below the x-axis. If our resultant vector was in the 1st quadrant, the reference angle is correct as is. If our resultant vector was in the 2nd quadrant, we would need to subtract it from 180 degrees. And if it was in the 3rd quadrant, you would need to add 180 degrees. But in this example, our magnitude for displacement is 30 kilometers and the direction is negative 38.5 degrees. Remember, unless a problem states magnitude only for displacement or velocity or any vector, you must also solve for the direction to receive full credit for vectors. Alright, last example. An airplane trip involves 3 legs, with 2 stopovers. The first leg is due east for 620 kilometers, the second leg is southeast at 45 degrees for 440 kilometers, and the third leg is at 53 degrees south of east for 550 kilometers. What is the plane's total displacement? Step 1. Break up each vector at an angle into components. Then step 2. Add up all vectors in the x direction. In this example, we have d1 plus d2x minus d3x. We break up d2x and d3x to get d2 cosine 45 and negative d3 cosine of 53. Plug in the numbers and we get 600 kilometers for the x direction. Step 3. Add up all vectors in the y direction. We have negative d2y and negative d3y. We can break up d2y and d3y into signs, and we get a value of negative 750 kilometers. Now that we know our resultant components, we can figure out the magnitude and direction of our resultant vector dr. By using Pythagorean theorem, we get 960 kilometers, and by using inverse tangent, we get 51 degrees. Again, our vector is in the 4th quadrant, so our angle is really negative 51 degrees. So our displacement has a magnitude of 960 kilometers and an angle of negative 51 degrees.